My name is James Taylor. And first, I just want to thank you guys for giving me the opportunity to talk to you today about Apache Phoenix. If my slide will advance, that is. OK. So first, a little bit about myself. I'm an architect at Salesforce.com, part of the Big Data Group. I've worked at Salesforce for about the past 6 years or so. I'm also the lead of the Apache Phoenix project. And I'm a PMC member of Apache CalSide as well, a project I'll talk a little bit about today as well. Before that, I worked for BEA Systems. Had my first experience with an Apache project called XML Beans. Worked a little bit on another product called Liquid Data, which was a federated X-query engine. Pretty interesting project. I also worked on WebLogic Event Server, which is has at its core a SQL-based complex event processor. And before that, I worked at various startups. So what I want to try to cover today, I want to start with just telling you what Apache Phoenix is. And then I'll move on and give you an idea of where we're at today, highlight some of the new features that we added in our recent 4.4 release. And I'll take a kind of a deeper look at how we do joins and subqueries. And then I'll talk about what's coming next, and hopefully have some time for some questions. OK, so what is Apache Phoenix? So I always like to do this. If you could just raise your hand if you're already familiar with Apache Phoenix. OK, not bad. More than last year. That's good. OK, so Apache Phoenix is a relational database layer on top of HBase. So it makes HBase look like a relational database. Part of it is a query engine. So what it does is it takes your query and it parses and compiles it. And then it compiles it down into native HBase calls as opposed to Mapreduce, which is more typically what something like Hive uses. It also pushes computation into the cluster to get maximum parallelization. That's part of what gives it its good performance. HBase provides a lot of hooks for this, which is really great. It lets us hook into server-side processing through something called coprocessors. It also allows us to push filters through custom filters that execute on the server side as well. We also have a metadata repository that we maintain as a separate HBase file. It's actually a Phoenix table itself. And so what we're doing is we're superimposing a SQL type system on top of HBase, which HBase is just a byte store. So we'll store your tables, your views, your sequence definitions, your secondary index definitions, all those kinds of things in that table, and we'll manage that table automatically. When you issue things like DDL, we'll update that table. But from your point of view, it's a JDBC driver, both a thick driver and a thin driver. It's up to you which one you want to use. We meet all the standard JDBC APIs, and we also meet the optional metadata APIs, so you can get access to your metadata that defines your tables as well. So we're also a top-level Apache project. We went through the kind of standard migration from an internal project to a GitHub project to an incubator. And a year ago, we became a top-level project. So it's our birthday. It's kind of exciting. And we've got a lot of momentum, too. It's pretty exciting to see how Phoenix has been picked up both within the Hadoop ecosystem in terms of Yarn is starting to use it. There's a work underway to combine Hive, CalSite, HBase, and Phoenix all together to make a kind of a more seamless relational database system. And there's also lots of interesting use cases I hear about all the time on the mailing list. So yeah, it's been fun so far. So here's how Phoenix fits into the overall ecosystem. So again, from your point of view, it's a JDBC driver. Those are the APIs that you use. One level below is a query execution engine. And then one level below that is HBase, and of course HDFS is under that, with Zookeeper doing the coordination. So that's the basic stack. OK, so where are we at today with Phoenix? We've really spent a lot of time over the past year and a half increasing our breadth of SQL support. We've had joins now for actually over a year. A lot of folks don't know about that, so we've got to do a better job of getting the word out. But I'm going to talk about that a little bit in detail. But we support joins, subqueries, correlated subqueries, semi, anti-joins, derived tables, all that kind of stuff that you'd expect. We also have secondary indexing. We have 3 different indexing strategies, because with big data and secondary indexing, kind of a one-size-fits-all approach doesn't work very well, we found. So let me tell you about those 3 different options. So the first is the most simple, and that's where you're adding a secondary index onto a table that you've declared as having immutable rows. So this is write once or append only data. So a typical use case would be log data, which typically has a time component as part of the row key. So rows are never being changed, they're only being appended. So for this case, the reason why it's more efficient is because there's no incremental secondary index maintenance that we have to do on the server side. Just as you append rows to your data table, we can do the transformation and append that same row to your secondary index table. So it's relatively simple. A second type of secondary indexing strategy is a global mutable for global mutable data. So this is kind of the secondary indexing that most of you are probably used to from the relational database world. So for this, what we rely on are coprocessors on the server side to keep your secondary index table in sync with your data table. So behind the scenes, when you create an index, we actually create a second HBase table that's ordered according to the columns that you're indexing. And then transparently, our optimizer will choose to use that table if it's deemed to be more efficient to do so. The third type of secondary indexes are for local indexes. So this is typically for write-heavy use cases. And let me tell you a little bit about local indexes. So we have something called a custom load balancer for local indexes that guarantees that all of the index data co-resides with your table data on the same region server. So the reason this is more performant for writes is because when we go to maintain those secondary indexes, all of your writes are local. So we can go ahead and do the data write and all your index writes on the same region server. There's no cross-region server traffic. This works for both mutable and immutable data. But the downside of this, and the reason why this isn't the only secondary indexing strategy, is because you take a hit at read time for these types of indexes. Because when we use this index, we don't know where a key is. So given a key range, we can't definitively know which region it's in. So we have to ask each region for the same set of data, and then the client will merge the results together. OK, another thing that we've developed are stats collection. So we piggyback on background processes in HBase that occurs during compaction and split time. And we write a Phoenix table that's tracking your stats. So what it's doing is it's finding equidistant keys within a region, a configurable byte amount. And based on those keys, we can use that on the client side to better parallelize your query. So for example, if you've got a query that's only hitting a single region, we can parallelize it perfectly based on our stats information. Okay, and finally, another area that is very important within Salesforce, which is where I work, is monitoring and management, just basically operationalizing Phoenix. So we've spent a lot of time coming up with both client metrics and tracing, which is both client and server, so that you can get better visibility into what's going on when a query is running. So tracing is pretty interesting. We build on another Apache project called Apache HTrace. And we use that to collect information across all the scans, because for any given query, we're parallelizing it. And so we'll collect information into our stats table, and we'll do this asynchronously, because that's how HTrace works. And then after the query runs, you can actually query the trace table through Phoenix to get an idea of where any bottlenecks may be, and where maybe index maintenance, where it's taking time, or where your queries are taking time. Maybe one region server is taking longer than others. Maybe it's an indication that you need to update your stats. So that's been super useful. OK, now let me take a little bit closer look at our join and subquery support. So in terms of grammar, we support all the things you'd expect: inner joins, left, right, full, outer joins, cross joins. We also support semi and anti-joins. That's a semi-join is where you use the in clause, and anti-join is where you use exists. So, and we support two different types of algorithms for joins. We support both a hash join as well as a sort merge join. Some of the optimizations that we do in the background are things like when you're joining together two tables where your primary key, where you're joining on your primary key, we'll use a capability that Phoenix has called a skip scan. So that'll be a much more efficient way of executing that join than doing a full table scan on both tables, of course. We also take a correlated subquery, and we'll decorrelate it and rewrite it as a join. So here's an example of a TPC query. Now, TPC, if you don't know what TPC is, it's benchmarking queries developed by an independent standards organization. And relational database vendors typically use these to benchmark against each other. So this is an example of one that calculates basically like an average yearly price. And it's a correlated subquery. And if you look, the top shows the query, and the bottom shows what our explain plan is, which is a little bit hard to decipher. But what it's saying, basically, is showing that it's taking the filter, and it's applying the filter before the join, which is what you want. That's one optimization. And it also took that correlated subquery, and it decorrelated it and turned it into a join. So those are an example of two of the optimizations going on with this particular query. Another example is a different TPC benchmark. This is doing both a group by and an order by on order priority. And it's a good example of also decorrelating, and also the optimization that I talked about where it executes a skip scan to join back from the line item data back to the order data, because your join condition is joining on the PK of the outer table. So this will execute very, very fast. There's still things that we can't do. So we don't have a nested loop join algorithm yet. And we don't really use stats yet to guide the choice of which join algorithm we use. And we also don't use stats to determine join order. We do it based on the order that you've listed your tables. So these are things we're going to do, and I'm going to talk about how we're going to do these things. OK, now, what's new in our 4.4 release? OK, of course, we've got HBase 1.0 support, which is great. We also have 1.1 support, which is awesome, too. We have support for functional indexes. So this was actually something that's available in our 4.3 release. I'll tell you a little bit about it. So functional indexes is where you're not just indexing on a column, but you're actually indexing on an expression. So take this query, for example. So by default, this is going to do a full table scan across your server metrics table. Maybe you want to know, maybe one day is there's more load on your system, so you're trying to hone this down, so you're executing this query a lot. So what you can do is you can add this secondary index, which is a functional secondary index. You notice what we're indexing on is a function of the create time instead of just the create time column. So now when you execute that query above, Phoenix will automatically use the index instead of the data table, and it'll do a range scan only for the day that you're interested in. Another thing that got added in 4.4 is user-defined functions. This is a really awesome feature. So basically what it allows is extension points to Phoenix. So what you can do is you can define the metadata of your function. You define the input parameters and their types and the output type. And you tell Phoenix where it can load the jar that contains the implementation for this function. And then leveraging an HBase feature, which will dynamically load jars, you can execute this example is a distance function, so it'll calculate the distance between two well-known landmarks, for example. So you could actually use this as you would any other built-in function in Phoenix. And Phoenix will even do all the optimization that it does today. So this particular query, it will actually execute on the server side. Another thing that's interesting about the user-defined function implementation is that it's tenant-aware. So what that means is if Phoenix supports multi-tenancy, and so when you define a user-defined function as a particular tenant, they're independent of user-defined functions that other tenants define. So there's no chance of a conflict. Okay, another new thing is a query server with a thin driver. So this is a really great feature that basically it allows you to run the query server node, the stuff that's compiling and optimizing your query and doing any client-side processing. It allows you to run that on its own server. So it offloads that. This is really important in environments like Salesforce, where today we run inside the app server's JVM. So that's a that's a shared resource that we can't really take full advantage of because we don't want to lock out other users of the app server. So now we can execute on our own server and do that much more processing. So the other side of this that's really pretty interesting is it minimizes the client dependencies. So now we don't have an ODBC driver yet, but it's much easier to implement one because all you have to do is write the same protocol that our thin driver is writing to our query server, and boom, you've got an ODBC driver. So that's at least on our roadmap now, which is great. So here's how you connect with the query server. Very similar URL, you just use thin in the URL instead, and then in a URL parameter, you specify your endpoint. And we have a server script that we bundle with our distribution that will start the query server. And that's all there is to it. One note of caution, this is a new feature, so the protocol between the client and the server is not really locked down yet. So we're not making any backward compatibility guarantees just yet between when you're using the thin driver. You can click through that URL for more information. Another item that we added is support for union all. So union all is just a standard SQL syntax where you can query multiple tables and get the results back in a single result set. So that was just another example of us increasing the breadth of our SQL. We open sourced a performance and functional testing at scale tool called FERF. So FERF is awesome. So the way FERF works is you define a scenario, which are a set of queries that you want to run, and you deploy FERF to your cluster. And you say what your data distribution should be for the tables that you're running over, and it'll generate that data and run all your queries and collect metrics as your sets of queries are running on your cluster. So it's completely geared at collecting performance data under actual multi-user scenarios, under representative data sizes. And it also can do functional testing, which is really interesting. So it'll output all of its data to a CSV file, and you can use that as your gold file. And then the next time you run it, it'll compare that and alert you if there's any diffs. So it's a good way to catch any regressions that only occur in a multi-user kind of environment. Okay, another thing, Mapreduce index build. So this is a great one. When you create a secondary index on a table today, if the table has a lot of data, then obviously it's going to take a long time to generate that secondary index. So now you could run that as a Mapreduce job instead of as just a single client API call. So that's really powerful. And it becomes monitorable and restartable as well, which is important. Another thing we have now is Spark integration. So what you can do is you can define an RDD that's backed by a Phoenix table. So that's a really awesome feature. And finally, we've done lots of new built-in functions, especially around dates. And transactions. So this is not in our 4.4 release, but it will be in our 4.5 release. I'll talk about this in a little bit more detail right now. So the model we're using for transactions is a snapshot isolation model. We're leveraging another open source project called Tephra, which is something that the guys over at Cask has done as part of their CDAP platform. We'll support a repeatable read isolation level. And we'll also allow you to read your uncommitted data, which today Phoenix doesn't show you your uncommitted data. You have to actually commit it first. It's optional, so if you don't want to use transactions, you won't take a performance hit at all. And it's enabled on a table-by-table basis. So it's a work in progress, but it's pretty far along. It's in a branch, the TXN branch. I encourage you all to give it a try. A little bit more detail about it. Again, it's optimistic concurrency model, so there's no locking involved. So there's no deadlock detection that's required. But the cost here is at commit time, there's a conflict resolution, a conflict detection that happens by the transaction manager. So that's the cost right there. It's a good model if the length of your transactions is relatively small. And it's also good if you can kind of have disjoint partitions that you're modifying. Like at Salesforce, we partition by org ID or tenant ID. So tenants only change their own data, so that it's a pretty good fit for that. And one interesting note is the conflict detection cost is actually not at all a factor if you've declared your table as having immutable rows, because by definition, you will never have a conflict. So here's kind of a high-level architecture view of it. On the left, you've got clients. Those are Phoenix clients in this case. And then on the right, you've got your transaction manager, which runs as a separate process. You can run multiple ones of those for automatic standby. Those use a zookeeper to do coordination and failover. And then the reads and the writes just go directly to HBase. As far as a transaction lifecycle, this kind of gives you a high-level picture of what that looks like. A transaction is actually started implicitly. As soon as you execute an update or a query, that your transaction is started. You can do as much work as you want. And then when you're ready to commit, you commit the data. The transaction manager checks for conflicts. If there are no conflicts, great, you're done. If there are conflicts, then it makes a callback on the client and gives Phoenix a chance to undo that transaction, essentially. So if the transaction is aborted successfully, great, then you're done. If not, then your transaction ID is actually placed on an invalid list, and then Tephra will automatically filter out data that that's on the invalid list, basically. So major components of Tephra are transaction-aware client. So this is surfaced, this is hidden from you, but from Phoenix point of view, it's surfaced as an H table. So there's an H table that implements transaction-aware. And that's what takes care of the coordination with the transaction manager. Then the next piece is the transaction manager itself, of course. That's the thing that assigns transaction IDs. Transaction IDs are actually based on wall clock time multiplied by a fixed constant. And the transaction manager is what maintains your state of your in-flight transactions or your invalid transactions. And then the final component is the transaction processor, which is actually implemented as a coprocessor. And what it does is the server-side filtering of any in-flight or invalid transaction data. And it also, at compaction time, will clean up any failed transactions. OK, so that's the full list. That is, I tip my hat to the community. This was an awesome release, really, to get all this done in a single release. Pretty exciting. OK, so what's next? So is Phoenix done now? We're almost getting close to SQL 92 compliance. We do joins. But there's something missing. I mean, what about the big picture? That's why you guys are all here, right? The whole Hadoop ecosystem. How can Phoenix be leveraged when it's more than just HBase that's involved in your data access? So yes, Phoenix has pretty good integration with some of these tools. Spark, I mentioned earlier, that's a new facility we have. We have Pig and general Mapreduce integration already. But it's a good story, but it's not yet great. So here's the big data landscape, right? It's huge, right? Where's HBase? Can anybody find HBase in here? So it's down there. Phoenix, it's not in there this year, but hopefully next year it'll be there. So how are we going to tie all this together? So we think the answer is with Apache Calcite. So this is a really interesting technology. Again, it's an incubating Apache project. It's a query parser, compiler, and planner, and optimizer. It's already SQL 92 compliant. And so right out of the box, it enables Phoenix to get the rest of the way there to SQL 92 compliance, which is really cool. It's also pluggable. That's its whole reason for existence. You plug in, as an adapter to Calcite, you plug in your cost rules. And then what Calcite does is it looks at all the possible plans that can satisfy a query, and it essentially picks the best one. So from our point of view, it's a sane way to do pushdown by defining your rules outside of the plumbing, which is a really powerful concept. The other reason it's really interesting is for interop. So it's not for free, so don't get me wrong. It's not like all of a sudden you're going to be able to query all these different data sources, such as Drill, Hive, Kylin, Samza, and Phoenix. But it is feasible, because now you've got one framework that they all live inside of, and they all define their rules in the same way. Oh, and don't forget about relational database sources. So I don't know about you guys, but Salesforce still has quite a bit of data in relational databases. So the whole idea is this one cost model to rule them all. I mean, take the best of breed. I mean, what if you want to do a query across JSON data that you can access through Drill, HBase data that you can access through Phoenix, and you want to join it through some historical data in Hive, and you've got some streaming real data that's coming in from Samza, and then on top of that, maybe you've got some OLAP cubes that you've built through Kylin, and you want to join them all together. I mean, this we think is a good path to that. So how does Phoenix leverage this? How does it plug into this? Well, instead of Phoenix having its own parser and compiler and optimizer, that actually gets replaced by the Calcite parser, compiler, and optimizer. And we plug in a little bit of SQL because Phoenix has some specific kind of non-standard SQL that it needs to be able to execute. And we also plug in our rules to the optimizer so that you don't suffer in performance. You see the same optimization happens today in Phoenix. And then at the lowest level, we generate a query plan, which is the same query plan that Phoenix generates today. It's just that we're using a different mechanism to generate it. So here's an example of some of the rules. The first 5 or 6 are standard Calcite rules that you get for free. An example, join commute rule. That's a rule that swaps join order based on your cost model, essentially. So that's a rule you get for free. Some of the Phoenix ones are specific to the way Phoenix can operate. For example, Phoenix can do a join. It can do a filter and a scan and a join all at the same time. So we have a rule that tells Calcite that. So Calcite can collapse a set of its logical steps into one physical step. So here's an example of that. So on the left, you see a logical plan that gets generated from a very simple join query. So you read this from the bottom up, basically. So at the lowest level, you've got 2 table scans that are going through a join operator, and then there's a filter, and then there's a project. So when you run this through Calcite and through Phoenix optimization rules, you get this physical plan on the right. So the interesting thing to note about this physical plan is it swapped the join order. So it did that based on the cost information it has on the stats that we keep. It also pushed the filter down to happen before the join, which is what you want. So then now we have a physical plan. So the next step is to take that physical plan and to generate the query plan that Phoenix knows how to actually execute. So that's the next step in the process. And so from this physical plan, we generate the standard hash join query plan, and we execute it. And so the runtime actually didn't change at all. It's just the compilation, the parsing, and the optimization changed. So this is one of my favorite examples. So this is back to the interop story, right? And this actually works out of the box, which is really cool. So this is a Phoenix table joining. It's a MySQL table. So Calcite is smart enough to know what Phoenix can execute and what needs to be executed by the MySQL adapter. And then it'll actually do the join. It's not as intelligent as it could be because it's always going to do the join, in this case, on the client, or on the query node, which is not necessarily what you want. But the facility is there to create rules that would define where and when to push the data maybe into HBase and do the join in the HBase side, or vice versa, depending on your cost model that is pluggable. So this is pretty exciting. Another example, this is mainly just to show this crazy with query, which I actually had never heard of before. Marianne Zhu pulled this up. But this actually, Phoenix will just execute now because Calcite just turns us into relational algebra. And this could be rewritten as a derived table query, essentially. And so we could just execute this, which is great. So why would you guys care? Well, you get better interop with tools because of this. Second example that's pretty interesting is the ability to support rollup, right? So Phoenix doesn't have support for rollup right now, but Calcite has a default implementation of rollup. So now, all of a sudden, you can do rollups in Phoenix, which is great. So that's pretty much all I got. This is a list of some of the users that are using Phoenix, some of the companies that are using Phoenix today. So if you want to be added to this list, then ping me. I'd be happy to add you. Thanks for your time, and I'd be happy to take any questions if there are any questions. And if you could use the mics, please.
You mentioned that you are using RDBMS also at Salesforce, and what percentage of that you still have data in the RDBMS? And if so, do you plan to migrate all that data into Hadoop and other?
Right. No, that's not the plan at all. So our relational store, this is not meant to replace our relational store. It's complementary. So it's for, big data use cases where your data won't fit on a single machine, for example. So that's the intention.
Where could we get more information on data modeling best practices for Phoenix?
It's a good question. So we have some of that on our website, but we need more. So if you go to phoenix.apache.org, you'll find some stuff. Not a great answer. Because, the point you're alluding to is, yes, it's different than the relational world. And
Yes.
right, and how should you do it? Best place to start is our website. Ping us on the dev list. We have use case questions all the time, and we try to help people model. Yeah.
Can I give you a quick example, and you might be able to tell me if I could maybe search the mail list or send you an email directly?
OK.
So, for example, we have some HBase tables where we have a number of column families. And for optimization reasons, the column families group together what I would call sub-primary keys for those column families. Then in the Phoenix implementation of that table, we borrow those kind of sub-primary key columns and roll those into the top-level primary key for the Phoenix table. So now I have the data appearing in, the same key data appearing in more than one row. I don't know if that's good or if that's bad. It's probably good from an HBase processing standpoint. I don't know if it's good or it's bad for Phoenix. I know that when the data comes back through JDBC, I can't always get the metadata to figure out which version of the data I'm looking at.
Right.
I would like to know if there's a way to identify the underlying column families, and then I'd like to know if this is a good practice or not. Maybe I should pull it out of the column families and just put it in the primary key, or?
It's definitely a longer answer than 2 minutes and 30 seconds. But catch me offline, and we can afterwards, and we can talk about it.
Okay, thank you.
Sorry. Question over here?
Yeah. Is there any plans for dealing with more of like, I'll say schema on read or like compact encoding? A lot of our different queries that we deal with, so we have a very large database or HBase installation, and so we're doing like a schema on read with a compact encoding on it.
Right.
And how we might be able to surface those then up through Phoenix, because right now we just basically are doing HBase APIs, and we'd like to take advantage of Phoenix over the top of that.
Right. So yeah, I didn't talk about that too much, but we've had this capability. We call it dynamic columns, but it's essentially you define the columns at query time, and then they're just like columns that you can join against or filter against. So that's one answer. Mm-hmm. Another answer is views. So you can define a view against an HBase table directly. So those are the two ways, I'd say.
Okay. One other quick question, just on Calcite.
Sure.
How do you see this as complementary to like Apache Lens, or as an alternative to that, or where you were showing like where you might be able to like join across like multiple different data sources?
Right.
Or where you can be able to plug in the optimizer, or do you see that complementary or just solving a different problem?
I'm not familiar with that project, so I have to. Apache Lens is called?
Yes.
I'd love to talk to you about it.
Okay.
Yeah. Hopefully complementary. There's not enough engineers in the world to be competing on stuff like that. Yeah.
I was wondering if you can tell us a little bit, or insights into SLAs, and let's say you had a table with 500 million rows, and I'm particularly interested in like group by operations and what type of performance you could achieve.
That's hard to generalize, really. I mean, it depends so much on your shape of your data, how updated your stats are, whether you have.
Have you done any performance analysis at that level?
Well, again, what I would encourage you to do, because all use cases are different, is use our use that FERF tool that I was talking about and load this up on your cluster. I mean, what we'd really like to do is have part of our website devoted to people having these type of discussions about here's best practices, here's what to do, here's what not to do, and here's the FERF scenarios that show that, right? So we'd like to start developing kind of a library of that. So, I mean, if you're interested in that, then we can help you set FERF up if you have any problems, and we'd love to get that information from you. I've got 30 seconds, I think. Oh, maybe. OK, I better move off. Let me take your questions over here.